Okay, great. So, welcome back. We are going to continue, as I said, by talking about window functions. You probably learned all you want to know about common table expressions and the many exciting things that they can do. And we're now going to talk about a capability of SQL that is more analytic. It's more related to analysis of data versus imperative control of SQL. This is an interesting talk. It's on the same website as my previous talk. So the part right here is the same. And again, you should find those slides if you wish. So what are we going to talk about? We're going to talk about an introduction to window functions. I'll explain a little bit about what they do. Then I'll talk to you about the syntax of window functions, which is sort of awkward. It's hard to explain, but I'll show you a lot of examples. Then we will talk about, again, the window function syntax with generic aggregates. I know that doesn't make any sense right now, but it will. Then we'll talk about window-specific aggregate functions. And then section 5, which I think is going to be the most interesting, is window function examples. So there's a lot of preparation work in this talk that has to explain a lot of things. But once we get to section 5, I think you'll be impressed by how many things you can do with window functions. And then finally, I'll give you some rules you can use when using window functions in the future. Just a housekeeping task, I looked at the schedule. It looks like we're scheduled to finish the entire conference at 17:15, and I assume we'll probably be finishing at that time as well. 17:15 is the scheduled finish time. And again, during this section, as in the previous, we'll be taking questions, and we'll give you the chance to look up things if you want. Okay. First, introduction to window functions. Window functions are part of a larger capability in Postgres that is whose goal it is to analyze data, called data analytics. Window functions are part of things like data partitioning. Here to use common table expressions, special indexing, parallelism, grouping sets, and so on, which are all there to allow you to analyze the data that's in your system. So window function is just one part of that. This is a section from the Postgres documentation that talks about window functions. I'm not going to go into detail, but there's just one sentence I want to highlight here. Basically, when you normally use an aggregate function, you expect to reduce the number of rows that you get. So if you do a sum on a table, it's going to sum several rows into a single row. If you do a count, it's going to count and return a single row as a count, okay, or an average. What's unusual about window functions is that they do not cause the rows to become grouped into a single output row, but instead the rows retain their separate identities. And you're going to see this over and over again. If you've ever had a case where you wanted to do some type of analysis of data, but you still wanted to retain all of the data rows, this is what window aggregates are for. And I think you'll find them to be very, very useful. Okay. Another thing to keep in mind that I use red. So again, if you see red in the query, that's what you should be looking at. Okay. So here's an example of a non-window function, just counts from 1 to 10, right? Uses a function called generate series, and it just generates numbers from 1 to 10. Another aspect that is very similar to the previous presentation is if you look at the URL down here at the bottom, you can download all of the slides for this presentation and run them in a query, and you can see the entire presentation output as one huge SQL file. So again, that option is available for you as well. Here is our first window function. Effectively, the reason we know it's a window function is because it uses the word over. Over is a special keyword that indicates that a window function is to be used. And normally, as you can see here in parentheses, after the word over, there is some text that normally goes between those parentheses. In this case, we're using the default, which means nothing, just use the default. But even if you just want to use the default, you have to still say open parenthesis, close parenthesis. Okay? So we've basically taken a normal aggregate function called sum, and we've made it a window function by using the word over. And if you take a look at the output down here from the generate series, you see the numbers 1 to 10, which is exactly what you would expect from generate series. Okay? But the second column, this sum column, is fairly unusual. It's 55. Why is it 55? Well, it turns out if you add the numbers from 1 to 10, the answer is 55. Okay, so that's why you get the 55 there. In a normal situation without the over clause, the sum would have returned one number, 55. The difference here is that all 10 rows have remained distinct. We didn't collapse all 10 rows into one row. The rows are still there. All we did was we have a new column which is reaching from the current row out to other rows and summing them together. So effectively, it's a way for a single row to look at rows in the same set, in the same frame, in the same partition, but not to collapse them, but for them to retain their original form. You can do two over clauses. Here's an example of an over, of a count using an over and a sum using an over. Obviously, the reason that the second column is 10 is because the count is 10. There are 10 rows, okay? And the sum is 55 because it's the sum, right, from 1 to 10. Okay? You also have the ability to name your window clause. So the parentheses that I used before, what I effectively did was I used a special clause called window, and I labeled that clause W, and now I can say over W and over W here, and effectively it's going to reference my window clause. Okay, so if you have cases where you don't want to repeat things, you can basically use a window clause there. I mentioned that when you use parentheses, you get a default. Here in red, indeed, is the default. It's a very cryptic set of words, which doesn't even mean what it looks like it means sometimes. Range between unbounded preceding and current row is the default clause that you get when you don't specify anything in the parentheses. And we'll be coming back to this, this red sort of section later on. I'll explain exactly what that means. So, any questions so far? Okay. Yes?
Does it start calculating the result from scratch for each row?
Right, so that's a good question. Does it calculate the result for each row? The way the window functions work is that the outer query is run first without the window portion, okay? And then based on the qualifications of the clause, it then, as a second stage, runs the window functions over that output. I can't remember if it recomputes it for every row. There are some clauses that have to be recomputed for every row. I'll show them to you in a minute. In this particular case, they don't need to be repeated. And I don't remember if we have an optimization to identify which clauses need to be recomputed. I don't remember I have a feeling they're recomputed on every row. I have a feeling that's true, but I'd have to look at the source code, I'm sorry. It would be an optimization that would be very interesting, yeah, so you don't recompute the same value over and over again. Yeah. Other questions? Yes.
Can you make a slide before, please? When I see current row with window close, I think I should get a result in some sense connected to current row. Why the summary columns are identical?
Yes, that is a great question. I will have the answer for you in 30 seconds. Yes, it's embarrassing, I think, yes. Other questions? Okay, yeah, in fact, I didn't tell you this at the beginning, but I started working on this presentation 6 years ago. 6 years ago, we added window functions to Postgres, and I thought, oh, this is interesting, I should write a presentation. And I got so confused at window functions that I gave up. In fact, I kept the queries, but for 6 years, they just sat in a directory because I could not really figure out how to present this material because I couldn't understand it. And this summer, I was home a lot. I didn't travel a lot. I travel 90 days a year, roughly. And from June to August, I was home. I didn't travel. I think I traveled 1 or 2 places. I didn't come to St. Petersburg, for example, right? I just, for some reason, I stayed home a lot. And I said, let me go back to this thing that I failed 6 years ago and try and understand it. And that was one of the things that confused me. And this time, I was able to understand it, and I feel like I actually got it. The other odd thing is that I've given this presentation to people who use window functions. And I've heard many, many times they said, I've used window functions for years. I thought that I understood them, but I did not until I saw this presentation. So it is a very dense presentation, very confusing, but I think it'll be clear as we go forward. So thank you. Other questions? Okay. This is the window function syntax. Again, I'm not going to talk about all the things here yet because we're going to go over them in detail later. But you have a partition by clause, you have an order by clause, you have a range of rows clause, you have a frame clause, and then you have these possible values for the frame. And again, at the bottom, we have a URL to the Postgres documentation, right, to give you current results there. Okay. So here's where we get into the interesting question from the gentleman. This is the default window clause. So the default window clause does not have a partition, does not have an order by, and uses range mode. And that means that the current row includes all the peers. This is just kind of for your text later, but we're going to get to why this is really confusing. Okay, so here's the first confusing part. You will see the word current row referenced several times in this presentation. What is very confusing is that current row in some places will mean exactly what you think it means. That is the literal current row that I'm processing. There are other times where it will mean any row that has an equal order by value to my row. So if my row is A, It may mean current row might mean all of the A's or all of the 7s, whatever the number, whatever the value is. It may mean everyone that has my same value in the order by clause. Okay? There are other cases where current row will literally mean the first or last row of a partition. I know it makes no sense why they did this way. I'm not sure why. Some people who understand mathematics better than me have explained that it's okay, but it is a constant source of confusion. So just be aware the word current row does not always mean what you think it means. Okay, and I'll show you specific examples as we go forward. So for example, current row means the current row if you're in something called rows mode. There's actually two modes you can be in. You can be in range mode or rows mode. Remember I said we have an option here, range mode or rows mode. When you're in rows mode, current row means current row. Okay? When you're in range mode, it doesn't. And range mode is the default, by the way. If you're in range mode and you have an order by, then current row means all of your peers, means all of the rows that have the same order by value that you do. Okay? And if you're in range mode and you don't have an order by, it means the first or last row of the partition. And that is why this query, which you asked about, when it says current row right there, it means the last row in the partition. Because we're in range mode and there's no order by. Very disappointing, but that's what we got. This is what the standard has, that's what we have to implement. Okay? So that's a little kind of background there. Any questions? Okay. Let's take a look visually. Okay, here's a data set where we have the numbers from 1 to 5, and they happen to be duplicated. Okay? So the literal current row is right here. Right? And that's the literal current row. The set of peers of the current row are both of the 3's. Those are my peers. Okay? If I define a window frame as rows unbounded preceding, it actually means unbounded preceding means this row all the way up to my current row because I'm in rows mode. If I do an order by, then it becomes my peers, and this is the entire partition. Okay, so to be more specific, rows current row to current row is actually just the current row. Order by X range current row to current row is actually my peers. Rows unbounded preceding to current row is unbounded preceding all the way up to my current row. Order by X unbounded preceding includes my peers, and this is the entire result set. Rows between unbounded preceding and unbounded following. Okay? And unless you see this video, I mean, we should not need to have a presentation to understand how to use this, but you unfortunately do. For whatever unfortunate reason, this is the cards we've been dealt. Okay. Any questions? Okay, so let's look at some examples. Here is the same generate series 1 to 10. Okay. And the same count with my count right here and my sum right there. We've seen this query before, okay? And as you'll notice, it's in range mode. What happens if I change the range mode to rows mode? Right? That's the 55s. Change to rows mode, I get what looks like some interesting output, but in fact it makes sense. Let's look at this sum here. So when we're saying rows mode, unbounded proceeding to current row, because we're in rows mode, current row is literally the current row. So, and we're doing a sum. So 1 plus 1 is 1. 1 plus 2 is 3. So that's the first row plus the second row. Okay? First row plus second row plus third row is 6. First row, second row, third row plus fourth row is 10. Okay? All the way down until we hit 55, because 55, as we know, is 1 plus 1 all the way to 10. Okay? Kind of, at least it's consistent. right? Now, because the default is with current row, I could have written it this way. I say rows mode, unbounded proceeding. And it's a, and current row is the default, so I get the same result. Okay. What if I say rows mode between current row and current row? Well, I'm in rows mode, so current row is literally the current row, and effectively every row is itself. And the count is 1, because it's one row of each, right? I mean, this, at least it makes sense. In rows mode, current row to current row literally means just the current row. All right? I can even type this. I can say rows current row and just stop there. Because current row and current row is the other default, so therefore I get the same result. Here's a different one. What did we do here, right? This is rows mode between current row and unbounded following. So instead of summing or counting from the beginning to the current literal current row, we're counting from the current row to the end of the set, end of the partition, end of the frame in this case. Okay. So the first row is 55 because it added 10 rows. The second row is 54 because it added 9 rows. Third row is 52 because it added 8 rows and so forth all the way down. And of course, the last row is 10 and it counted 1 row. Any questions? Okay. This one's interesting. One preceding. What does that do? Well, when you use the word preceding, you're saying preceding relative to the literal current row. So what I'm doing here is I'm asking for count star, which it counts nulls. I'm looking for count x, which doesn't count nulls. And I'm looking for a sum. And I'm doing it from the row before the current row to the current row. Right? And as you'll notice here, the current row 1 is just 1 because there is no preceding row. Okay, there is no row before it. Row 2 has 2 rows before it, and it actually sums to 3. Row 3 has 2 rows before it, and it sums to 5 because it's 2 plus 3. Row 4 is 7 because it's adding 4 plus 3, and all the way down. Okay? I can do one following. So I say the next row. So this is 3 because it's 1 plus 2. This is 5 because it's 2 plus 3. This is 7 because it's 3 plus 4 and all the way down. And when you get to 10, there's nothing after it, so it's just 10. All right? I can do 3 preceding, and it would count all 3 of them before. So 1 is 1 because there's no row before it. 3 is 3 because there's only 1 row before it. When I get to 6, this is also 1 plus 2 plus 3. When I get to 10 now, I'm counting all the way back here, right? 4 plus 3 plus 2 plus 1 is 10. 14 is 5 all the way to 2, and so forth all the way down. So it's going 3 back and including the current row and doing a count. What if I add an order by? Remember we talked about order by as a capability here. So what I've done is I've added an order by in the clause, and now when I do my query, because I have an order by current row, you remember I told you way back here, I will go back to that slide. I told you way back here that current row, if you have an order by and you're in range mode, is the current row plus all of its peers. So what happens as soon as I added the order by, it changed the meaning of the default current row text. Okay? Good. I'll take the one nod. So what I'm doing is I'm still using the default clause, unbounded proceeding to current row. But because I've added an order by, current row doesn't mean the end of the set anymore. Current row means myself and any of my peers. So in fact, looking at this, you basically get unbounded proceeding to the literal current row because the order by is now there, and that's what you'd expect. Okay? Again, at the bottom. Current row peers are rows with equal values in the order by columns, or all partition rows if order by is not specified. Okay? And again, this is the full specification here, order by range between unbounded proceeding and current row. Right? That's exactly what is happening inside there. And the presence of the order by has changed the meaning of current row here. All right? Any questions? So, what if I use the order by clause and I just say range current row, and in fact, because current row is literally all of the peers and all the values are unique, you basically just get 1 to 10, right? Kind of interesting. So, let's switch gears a little bit, and let's take a look at a table with duplicates. All right, because right now you can't see the peers because every row has the same value, right? So we're going to create a table 1 to 5 with duplicates for every value. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And this is going to be better illustrative, I think. So, same query, window, function, parentheses, use the defaults. I get now the total of 30. So 30 happens to be 1, 1 plus 2, 2 plus 3, 3 plus 4, 4, 5, 5, all the way added up. Okay, this is exactly what we would expect. Here's where it gets a little interesting, and I've used colors here to more clearly show you the behavior of the peers. Remember, if you don't supply a frame clause, it's unbounded proceeding to current row, and because we have an order by clause here, current row means all rows that have the same order by value, all of the peers. And that's why you see the same number repeated twice. Because this first row can see itself and the next row. The third row can see the third row and the fourth row because those are both peers. Okay? And that's true all the way down. They're now seeing peers and they're going down, and the frame clause for the sum is actually including the peers. If I change, and this is exactly what the defaults are, right? So you're seeing the little defaults. Now, if I change that to rows mode, you might remember way back earlier I said, when we go into rows mode, current row literally means current row again. It doesn't mean the peers. And therefore, row 1 can just see row 1. It can't see the second row. Row 2 can just see row 2, row 3 can do, and you can identify that the counts. Because if you look back at the counts here, they're all seeing the next, all of their peers, all the way down. Here they're not. They're only seeing from the beginning of the set to their literal current row. And the totals also reflect that. This is 1. This is 2 because it's 1 plus 2. This is 2 plus 1 plus 1, it's 4. This is another 2, it's 6, right? So as soon as we went into rows mode, we lost the peers capability and we switched to being literal current row for this query. Okay? Here's the same query, a little different. We're back to range mode, and we're doing current row, basically current row to current row, right? So every row sees 2 rows because they see their peers. Remember, current row in range mode with an order by is all of the peers. So it's from the beginning of your peers to the end of your peers, right? These both see 2, these both see 2, these both see 2, all the way down. So this is 2, 2, 4, because it's 2 plus 2, 6, because it's 3 plus 3, 8 plus 8, 4 plus 4, and 5 plus 5, all the way down. Okay? If I switch to rows mode, I get a completely different output. Again, in rows mode, current row means current row to current row, so therefore you're getting just the numbers. Each row only sees one row, and the sum is just itself. Very, very trivial. Okay. Now be aware, we are going to get to some examples which give you practical uses for these. Okay, when we get to there's that section 5 I talked about is really where it starts to get interesting. We have to do this sort of mechanics so we can understand the later sections. Okay. Very similar to common table expressions. We started very simple, right? And then by the end, you're like, whoa, right? It's the same kind of a presentation. Okay. Another clause that we have is partition by. Partition by allows you to break up your set into partitions, and the partitions themselves allow you to group the rows together. So if I partition by X, every row value becomes its own partition. That's why all these counts are 2, and again the totals reflect that the partitions are now broken together. This is kind of a trivial example. This is a better example. What we've done here is we created a partition for all of the values greater than 2 and all of the values 2 or less. Okay? So in red, we have the values 2 or less, and in blue, we have the values greater than 2. Okay? And if you take a look at the way this is designed, you will notice that when we do our counts, you do not leave your own partition. So for example, because we don't have an order by, and we're in range mode, we're totaling the entire partition. So 1 plus 1 plus 2 plus 2 is 6, and all the rows are 6. Just the same in the beginning when everything was 55, right? Now everything's 6. But we're only in that little partition. Here we have 24, because in fact 3, 3, 4, 4, 5, 5 added together is 24, but they're in their own partition. Okay? If we add an order by, then current row now means current row and its peers. So the first 2 rows see 2 rows, the second 2 rows see 4, and the counts are reflective of that. If I switch, and this is what it is with defaults, again, each row sees its own peers. And if I switch into rows mode, you can see I'm going back and forth here. This is range mode, that's rows mode. Because of course rows mode is not going to count the peers, current row is literally going to be the current row. Okay? Oh, that's 1, 2, 3, 4, and as you'll notice the second partition starts from 1 again. So the queries never span partitions. Any questions? Let's stay here. Any questions? Okay. So let's take a look at another set of functions that you probably have never seen before, and that is the window-specific functions. Up to this point, I've used generic aggregates that you're familiar with, things like sum and count. Okay? But there are a whole set of functions that were designed specifically for window processing, and those functions I am going to talk about in this section. So, the first function is called row number. It literally just numbers the rows in the window, in the frame, and in fact I'm just taking my original set here, and I'm just calling row number, and it's just going 1 to 10. Okay? Row number doesn't take any arguments, and it actually operates on partitions. What that means is that it doesn't matter what you specify as a window frame. Range mode doesn't matter, rows mode doesn't matter, unbound to preceding, current row makes no difference. This function operates on partitions, doesn't matter what your frame specification is at all. Okay? And again, we have a URL here at the bottom if you want to look at the Postgres docs on these functions. Okay. We have another function called lag. It allows me to look backward Similar to one preceding, except that it allows me, it's a little more flexible. So now I'm doing lag, and I'm saying give me the row before my row. Right? Give me the row before my row. Here I'm saying, okay, this is 1, and this is null because there is no row before it. But the next row, the 1 is 1, and all the way out here, it just shifted everything 1, basically. Okay. I can do lag 2, and then I'm going to go 2 backward from my current row. Again, first 2 rows don't have any rows there, so they return null. Okay. There is another function called lead, opposite of lag. It says give me the rows ahead of mine, in front of mine. Okay, or they come after mine. Let's put it that way. So here I'm doing a lag, and you can see I have no values here. And here I'm doing a lead. I'm basically shifting everything up by 2. And when I get to 5, I don't have any rows, so it ends up being a null. Again, these operate on partitions. Doesn't matter what your frame clause is at all. Okay. You can also specify defaults for some of these if you wish. Another function, first value and last value. These allow you to specify the first and last value in a window frame. Okay, so in this case, give me the first value x in this frame, and I'm getting 1, and then give me the last value x. Now, keep in mind this is operating on window frames. So therefore current row, there's an order by, so current row means the current row, so it's unbounded proceeding to current row. That's my frame, right? That's my default frame. So I can't ask for the last value in the partition because my frame is smaller than the partition, okay? If I change it, if I change my partition from being the default to actually saying unbounded proceeding to unbounded following, now my last value literally is the last value in the frame because I open my window frame up. It's the last value in the partition because I open my window frame up. Okay? I can do something called nth value. It means give me the nth value in this particular frame. And here I'm asking for the third value here in the frame. This is a little interesting. I'm asking for the 7th value in the frame, but you'll notice that until I get to the 7th row, I don't have a 7th value in the frame. Why is that? Because I have an order by, and because my default frame is unbounded proceeding to current row. Again, if I open, and this is the defaults, okay, and that's why, if I open up my window frame to be the entire partition, now no matter which row I ask for the 7th row from, I get the 7th row value. Okay? Any questions? So, here's another window-specific function. It's related to something called ranking. What ranking is designed to do is to place the values in a certain ordering and number that ordering. So think of, people who finish a race, the first place, second place, third place person in the race. Okay? Now in this case, because these operate on a partition, unfortunately, because there's no order by in this query, it doesn't know how to rank anyone. So there's no order by, so I can't rank them, so it thinks everyone finished first. Wonderful, right? You haven't told me how to rank them because of that. So if I take the parenthesis there and I add, I use the defaults, again, there's no order by, so therefore there's no ranking involved. Even in rows mode, again, there's no ranking. But if I add an order by, then I can get some ranking. All right? What you can see is we're ordering by X, so therefore the lowest values of X are the highest ranks. And you'll notice that the first row gets a 1. Now the second row, because it's identical value, also gets a 1. And this is the problem if two people finish a race at the identical time, they pretty much both get first place. There's really nothing you can do. I mean, they can try and figure out which one, but if they're literally at the same time, then they're both first place. What's interesting about this particular case is how do you handle the next person to cross the line? So if two people cross the finish line at the same time, the next person to cross the finish line, is that person second or are they third? It's really not clear how to handle that, so the SQL Standards Committee gives you two ways. If you use the rank function, then the next person to cross the line is third. So you have two first place finishers and a third place. Okay? With dense rank, you basically have a case where you have two first place finishers and the next person to cross the line is second. So again, depending on how you want to do it, you can very easily handle that ranking. All right? Question? Another really interesting feature of this system is something called percentile rank and cumulative distribution. And what these are trying to do is to tell you for a given value what percentage of values are less than my value. So given my value, what percentage are less, what percentile rank does is it says what ratio is less than me, excluding me, and cumulative distribution says all the rows that are equal or less than me. Okay? So if I take a look at this 1, for example, what percentage are less than me? 0. For the 2s, what percentage are less than me? Well, 22%. If I exclude myself, which it says it does, what percentage are less than me? Well, it turns out it's 2 out of 9 are less than me. Okay, no, I'm sorry, 2 out of 9, 2 out of 9 are less than me. And the same thing all the way out here. Cumulative distribution is a little easier. What percentage are equal or less than me? That would be 20%, in this case 40%, and then down here 100% are equal or less than me. So again, I'm not sure which one is better, percentile rank, cumulative distribution. I'm not really happy with either of them, frankly. I think there should be something that counts half of the ones that are equal to you. Like, for example, if I got a score on something, I'd like to know how many were less than me, and then half of the people who were equal to me. And that would give me kind of a better number, I think, than either of these two, but there's no way to compute it. I guess you'd have to create your own function to do it. Maybe someday. The last function is entile, and it will break the set up into, in this case, 3 similar sized groupings. So if you think the top third, the middle third, the bottom third, that's kind of what entile, or quarters or whatever, that's what the entile function would do. Any questions? So if we use partition by with this rank and dense rank, you can actually see the behavior here. In the first partition, this one was first, and again, depending on whether you use dense rank or rank, you get different values down here. And then for the next partition, we start over from 1. Okay? Start over from 1, and we basically, again, this is a completely different partition, a different set, and they get new rankings within that partition. Here's another example. It's just using percentile rank and cumulative distribution and entile within partitions. Again, similar behavior. What percentage are equal or less than? What percentage are less than excluding myself? Okay. That excluding myself phrase is kind of odd. There's some reasons maybe why it's there, but I'm not positive. I was told that Russian statistics has a tendency to do things more that way than maybe Western Europe, North America style, but I don't know if that's true or not. But those are the functions we got, those are the definitions we got. Any questions? Yes?
Why we have null in this case? I apologize for lost question.
So normally Postgres would not display the word null, it would just put a blank. But I put the word null there so you really knew it was a literal null. Is that your question? Just why is the text there, or why is it saying a null? So the reason this is a null is because the nth value works on frames, and there is no seventh value in the frame until you get to the seventh row. It can't see beyond the frame you've defined. And because the frame is defined as order by x, range between, the frame is literally the peers of x, and in this case you don't get to the seventh row until you actually are on the seventh row, and then you can see it. But if you look at this row can only see 3 rows. So there is no seventh row.
Thanks, yeah.
Oh, sure, of course. It is very awkward, yes.
Partition by support dividing only by 2 partition, or we can specify some other statement?
So if you look at this example here, I'm partitioning by every x value. So in this example, every x value has its own partition. And that's why there's, I'm sorry, where is it?
Okay, thank you.
Right, because if you look, well, you can't see it there. Hold on, let me back up here. I think I had a better partition example. No, I didn't. Hold on. No, it was up here, sorry. Yeah, so here, every partition, every x value has its own partition. Right, because every count is 2, so it sees only its peers, basically. Okay, and then the other example, I just made 2, but you could make it 3. Effectively, all it's doing, if you take a look, is it's making an integer of 0 or 1, right? But if you just said modulus 3, you'd create 3 different partitions with your rows. However you want to do it. You could do almost anything. Okay? Other questions? Okay. Great. Now, so this is where we start to really kind of go, where we start to make use of this, and we have actual examples, and I think you'll start to see the practical use of the window function. So, to start out, Let's create a table called EMP for employee, okay? And we're going to put 7 employees into this table, okay? So create an empty table, put 7 employees in, all right? This is what they look like. They have departments and they have salaries, all right? So we could do a generic aggregate like this. We could say, how many employees do we have? What is the sum of the salary? And what is the average salary? And of course, in this case, we get one row because these are not window functions. These are just aggregates. There's no over clause. There's no window clause, right? Very, very generic, right? We can do this. We can say group by department, order by department. Again, not a window function, no window clause here, okay, no over. And we're just saying for every department, how many people in each department, what's the sum of the salary in that department, what's the average salary in that department. Okay? Pretty easy. We can even use a function called rollup. Rollup will actually give me the total of each department, and then it'll give me a total for the entire set. Still not using window functions here, right? That null there at the bottom is giving me the total of 7 employees. It's combining the one query with the group by query, basically. That's what rollup does. All right? Still no window functions. I can order my output by salary, who gets the most money, who gets the least money, and so forth. Okay? Here's my first window function. I'm doing an over on salary. Do you remember way back in the beginning we had the 55, just went straight down the thing? Well, that's exactly what's happening here. It's taking the salaries, just totaling the whole thing up. Not very useful, but it works. Okay? We're just summing up all the salaries. And remember, we're using the default window clause here, right? There's my default window clause. And we know when we do a sum over the default window clause, we're going to get the total of everything. Now you might think that's not very useful, but you could do this. You could say sum over everything, which says give me the sum of everyone. But also what I want to do is I want to divide the salary by that sum now. So now for each employee, I can see what percentage of the total salary they are, right? So that gives me some use to that sum now, because I'm dividing each salary by the total. Great use of window functions, because I still have my 7 employees. I didn't lose the distinctiveness of the employees. I allowed that employee to be compared against the total of all of the employees in that set. All right? I can do this. I don't know why you'd want to, but it's kind of interesting. I can say take the sum of the salaries, order it by salary, and then basically go into rows mode, which means unbounded proceeding to current row, and effectively I have a cumulative total of salary as I go from the most expensive to the least expensive employee. Now this is probably not very useful for salaries, but something like a rain amount or amount of coal we mined every day this month, and you might want cumulative totals of rain over the month, something like that. These are very useful kind of queries to write. Okay? Any questions? Here's another one. This is, again, looks pretty trivial. I have my name, I have the person's salary, and then I have the average of all of the salaries, right? Doesn't seem very useful. It's the same number in every row, blah, 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 blah. But what if I do this? What I'm now showing is the difference between that person's salary and the average salary. In red, I'm showing all of the people who have a salary above the average. And in blue, I'm showing all the people that have a salary below the average. Okay? Kind of interesting. I could do this. I could say, take the current salary and subtract it from the next salary. So how much more, if you look at the employees in order, how much more money does that person make than the next lower paid employee? Right? So Mike is 500 more than James, 300 more than Betty, 900 more than Sandy, 900 more than Andy, 900 more than Tracy, 200 more than Carol. Okay? So you basically have this sort of stratification. You can see the differences as you're going down. Here's a even bigger one, which I'm going to have to walk you through. So we have the name, okay? We have the salary. Then we have how much more that person is making than the lowest paid employee. So in this case, the lowest paid employee is Carol, and we're asking how much more is that person making than the lowest paid employee. And the last column says, what percentage more are they making than the lowest paid employee? Okay? So in this particular case, Mike is making 54% more than the lowest paid employee. All right? And as you can imagine, they get smaller and smaller, and Carol is making 0% more than the lowest paid because unfortunately, she's the lowest paid for whatever reason. Okay? So you can kind of get an idea of how that stratification is happening there. You're seeing the total amount more than the lowest paid employee and the percentage more. And the way we're doing that is using last value. And we're also having to define a window frame that contains the entire set. Right? So we can get to the last value in the partition. If not, we wouldn't be able to get to it. Make sense? I could do this. I could say, what is the ranking of these employees in terms of salary? Of course, Mike on number 1. James and Betty, again, have unique salaries. Andy's an interesting case. Andy and Sandy, both of them are making the same salary amount. So the next person in rank, if they're both making the 4th highest salary, would be 6, and in dense rank, the next rank for that person would be 5, because again, we don't allow gaps in the ranking in dense rank, right? We learned this already. Now we're actually seeing it with a real example. This one is really kind of eye-popping. What it's trying to do, and again, this is a good example of partitioning by department, which the lady asked about. We're trying to look at the employee, their department, their salary, the average for that salary, the average for that department, okay, not the average for the whole company, the average for that department, and how much different is that person's salary than the department average, right? So, Mike is 400 more than the department average, Betty is 400 less than the department average, okay? Sandy's 400 more, Carol's 400 less, James is 1,000 more, that's surprising. Andy is 200 less, and Tracy, unfortunately, is 800 less. Notice that, yeah, obviously Tracy, I think Carol was the person who made less money, but in fact, she's doing better department average-wise than Tracy is. Just interesting to see. This is kind of hard to write this in an application. Like, if you had to write an application to show this data, it's just kind of awkward. Yeah, like, oh, okay, what's my department? Okay, how many people do I have? I mean, I wouldn't want to write this, let's put it that way. My point about window functions, I would much rather just throw this problem at the database and say, just give me the answer I want, right? I mean, this is a great example. If I had to write this myself, I mean, I could do it, but if I could do it in Perl, I'm like, okay, get all the employees, what are my department, what unique departments do I have, what's my average for that department, okay, let's separate it out, so go through each employee in that department, subtract them, and like keep a track of where they are, and then I'm actually making a table in Perl. I'd much rather let the system just give me the table I want and be done with it, right? I think this is one of the real strengths of window functions, and again, I'm trying to show that in these slides. Okay. Here's another example. You might notice here that I'm saying partition by department over and over again. So what I did here is, I'm just going to make a window function, call it D. It'll be partitioned by department. I can just say over D now, right? Make it real easy. Just save me some typing. Okay? And of course, if I had a window clause, a range clause, or unbounded proceeding, all that could go in there as well. Okay? This is a little different. Now, the previous one, this one, gave you the difference between that employee and the average salary in that department. This one gives you the difference between that employee and the next less paid employee in that department. We're not comparing against the average now, we're comparing against the next employee in rank. So, in this case, I'm saying salary minus lead, meaning the next row in that partition, okay? And I'm ordering by salary descending so I can see all my rows. And effectively what happens here, again, I'm operating inside my partition, but lead, as I remember, it works in partitions. It doesn't care about frame clauses. So effectively, now Mike is making 800 more than the next person in the department. Betty, because she's the lowest paid person in that department, doesn't have a compare against, right? Sandy is making 800 more than Carol. Carol, again, unfortunately, doesn't have anybody less, so she has no value there. James, 1,200 more than Andy. Andy, 600 more than Tracy. Okay? So you got to kind of get the idea of how that kind of works. Right? We're not comparing against the average. We're not comparing against the next person with the next ranking salary. This is an interesting one. What it's showing me now is the ranking of the employee within their department, and then the ranking of the employee within the company. And what I'm trying to highlight here is that I can have different partitions, different window clauses for different columns. In fact, I could even mix them up. I could have a computation in a single column that uses different partitions and different window clauses, if I wanted to. I don't have an example of that. But here, for example, this is rank over S, which is partitioned by department. This is rank over everything. Again, ordered by salary. Okay? So you can see, these are their ranks within the departments, and here are their global ranks within the entire company. Very nice. Questions? Yes?
Is the employees able to start once on the executive store? According to the plan of request, how many times is the EMP able to start?
How many times is employees table full scanned?
I'm sorry, how many times is the table scanned? Thank you very much. I'm sorry, the scanned word I couldn't get. So the way that Postgres implements window functions is that it effectively creates, it runs the query, and then once the query is finished running, it runs the window functions over the result that you have. So it's really not computing, how do I explain it? It's not really rescanning the table, it's just taking the result set. It computes the result set without the window functions, and then it just uses the rows it has to compute window functions on top of that result. So the answer that you're probably asking is that window functions have very little impact on performance. I've never heard people complain that they're slow. It's certainly much faster than trying to do it in a client application, but they're pretty fast. You don't see them as a problem for performance. Everyone asked that question though. Thank you. Other questions? Okay. Everyone's gotten quiet all of a sudden. I think they're tired. It's getting late. I agree. Anyway, so let's just finish up here, and again, I'll be available to answer questions. I just want to give you sort of a general understanding of window functions kind of going forward. This is a beautiful picture. I wonder where that's from. Anyway, the link there down at the bottom would kind of tell you where you can find that picture. So when you're creating window functions, here are some suggestions. First, are you going to want to use partitions? So you're going to want to split up your data. That's probably your first question. Okay. Secondly, is there some kind of ordering in that partition that you want to specify? Third, how do you want to handle rows if you're using order by? How do you want to handle rows with the same order by values? You really have to think about this. Do you want to use range mode or do you want to use rows mode? And if you're using rank, do you want to use rank or do you want to use dense rank? Because both of those would relate to how you handle duplicate values in the same row. Okay? Do you need to define a window frame, a separate window? Is a window frame important? Maybe not, maybe it is. Window functions can define their own partitions, ordering window frames. So again, you can mix window functions. Each function can have its own window frame, specific window frame, specific order by, specific partition. You can specify multiple window names if you wish. I didn't show an example of that, but you can. And then pay attention to whether the window functions operate on frames or partitions, specifically this slide. So this is a summarization of the slide that we saw, the things that we've seen so far. Keep in mind that the first group operate on frames. And that means that when you specify rows mode, range mode, unbounded preceding, unbounded following, current row, those functions here are all going to be affected by the frame that you define. Okay? The functions down here at the bottom, they don't care about the window frame at all. They're going to operate on the partition. Lag, lead, row number, the ranking functions, and tile, cumulative distribution, all are going to be basically operating on the partition level. Doesn't matter what you do with frames, it's going to be the same. Okay? Keep in mind that a window function will never process data outside its partition. But in most cases, the partition will be the whole set if you haven't specified a partition. Okay? So that is the last slide. It is 5:06, so we're a little early. I'm happy about that. I hope you found this interesting. Again, my goal was to give you, as application developers, of an understanding of the power of SQL. Not only the power of the queries that you currently are using, but the ability to use imperative, recursive, and common table expressions well, and the ability to do window functions, which saves a lot of work on the application side in computing some of these complex reporting requirements that people have. And I tried to show you specific examples of both common table expressions and window functions, showing you why they would be useful. So, any final questions? Yes?
When I don't want to use window function and use ordinary statement without window function. Thank you.
So the question is, when would you want to use window functions and when not to use window functions, right? I think if you want a row to do some type of computation or behavior based on other rows in the set, you have to use window functions. That's really what I said way back kind of at the beginning, that effectively what the window function allows you to do, if you think of all the examples I showed you, we allowed the value on a row to be affected by other rows that are in the set, but we didn't want to collapse all the rows down into a single row, right? And for me, that's the beauty of it. If you just want a sum, and you want one row out, you just want the sum by department, no reason to use a window function, right? But if you want to somehow reach outside your row, but you still want each row to appear distinct in the output, that's really where window functions make sense. Other questions? Okay, you have a great evening. Thank you.